All right. So we have momentum practice, free response questions, the second set, first problem in that set. Not a bad looking question here, actually, in this first part. Creative. So we have this card A has a mass M, and card B double the mass. Card A is at rest at two heights or two H's above, and the one with two masses is 1H above. They give the angles. I'm not so sure that the angles make any difference. I think they might be a red herring because, as we know, it's really your starting height. You'll end up going the same speed at the bottom if you start at the same height. So even if this one started way back up here, it would end up so that its height was the same. It would end up, even though it has a shallower angle, going the same speed. I might be wrong, but I don't think the angles matter. Card B has a mass of 2. Okay. When carts roll towards each other, have a head-on collision on the horizontal portion of the ramp, and stick together. The masses of the carts and the wheels are negligible, as are any frictional drag losses or drag forces. Indicate whether the carts remain at rest, move to the left, or move to the right. All right. So we got to get some information about velocities down here. And that's going to come from kinetic energy. That's going to come from the fact that the potential energy up here at the top for each of them, so we'll say UGB and UGA, that is going to end up being the velocity, the kinetic energy at the bottom. And we have to solve for that kinetic energy in terms of their initial conditions. And that'll tell us who has got bigger velocity. And then we'll pair that with their masses and see who has more momentum. So let's start with the cart A. So we'll go down here. We'll start with cart A. And it's the idea that its mechanical energy at the top equals the mechanical energy at the bottom. But of course, that means the potential energy at the top, which is big M G 2H, equals the mechanical energy at the bottom, which is kinetic, 1/2 big M V. Subscripts make all the difference in the world. Velocity of cart A at bottom. As before the collision. Because after they collide, they're going to have a single velocity between them. So I'm going to solve for this. Now, it's a little bit convenient because the halves go away. I mean, not the halves. The masses go away. If I multiply both sides by 2, I get 4GH equals V, velocity of A at the bottom, squared, which means 2 times the square root of GH is equal to the velocity of AB. So AB being block A at the bottom. I'll write OT there, so cool. So we'll keep that in mind. We'll come back to that. We're going to use that and the mass to figure out its momentum down here. But let's go look at this transition for cart B as well, from potential to kinetic. Do the same thing. Cart B has a potential energy of 2mgh, and it would have a kinetic energy at the bottom of 1/2 2m velocity of cart B at the bottom squared. It's a sharp pencil right there. Then well, the m's go away, the 2's go away. So I multiply both sides by 2. Interesting. So I have 2gh equals velocity of cart B at the bottom. So what's interesting here is that while this one has double the mass doesn't end up making a difference in this situation because there's mass in the kinetic energy as well. Gravity will speed up any mass at the same rate. So that's why the 2's cancel out here. Whereas over here, this one had twice the height, and that 2 didn't go away because there wasn't a companion 2 over here. So we end up with square root of 2gh equals the velocity of block B at the bottom. All right. So B is moving slower because 2 times GH is more than square root of 2 times GH. In fact, it's a square root of 2 factor off. So now we have enough to look at the two carts as they approach each other here on their momenta as they approach here. So let's turn this page over and let's take a look at those carts. So we have one of them has a mass m, a velocity of and this was cart A at the bottom, of 2 square root of GH. Double check that. 2GH, yep. And it's headed this way. And the other cart has a mass of 2m, and its velocity headed this way is going to be square root of 2GH. So, the momentum before the collision is, well, let's take a look at it this way. This is the bigger number, right? So, the bigger number is positive. The smaller one would be negative if we decide to make this way positive and that way negative. So what this tells me right away is that this has more momentum, the magnitude of it, than this. That means when they're done, the leftover, the difference between these two, is going to be in that direction. So my initial thought is that they are going to be moving to the right. And that's probably how I would check it. Let's see if we can verify that. So the initial momentum is 2 square root GH minus square root of 2GH. They use a big H, don't they? Okay. The final momentum has to be the same, but the final momentum, usually I write it to the right, but we'll do it here for a second. The final momentum is the two of them stuck together. So, I didn't put the masses in here. So we'll put an M here and a 2M here. Actually, let's take a look. So I have an M times a 2. M times a 2, that's the same. Here I have 2. Ooh, now I'm not so sure. I was just basing the earlier thing on the velocities, but if you look at it, I have... Here, let me clean this up a little bit. By the way, this is why I like doing this without actually knowing the answer. Because I want you to see my process, and I want you to see the discoveries I make as I go along, going, oh, wait a second, because this is one of them, I think. Let's see. Clean this up. I got 2m. Now, the 2 in this case came from the velocity times the square root of GH. Whereas over here, there's a 2 that shows up because of the mass. So I have 2m times the square root of 2GH. So interesting. Now, this one looks like to me, it's going to be bigger. Over here on the right, this one. Because it's got an extra square root of 2 times it. So this is actually, I think, going to win. And I think that means it's going to go to the left. But let's see. Let's see if we can prove it, other than just looking at these two and thinking that's got to be the bigger number. The final momentum would be the sum of the two. So it would be 3m times a new velocity at the bottom, final velocity. So I guess it really doesn't tell us much, other than I'm looking at this, and and you can even plug in numbers real quick. It doesn't matter, right? So if I plug in a mass of 3, this is always a helpful one. G is 10, of course. H is, why not? Why not make H 1 meter, right? Then if I do that, I get 6, 10 times 1, 6 times the square root of 10 here. And here I get 6, 20, 6 square root of 20. And that's going to be a bigger number, and it's negative because it's the one going this way. So I would expect my final velocity to be to the left. Okay, so based on that, I would say they would move to the left. And this would be my explanation. Hopefully they would understand it. Okay, so let's go on to part B. Cart A has a mass of m and is released from rest from a height of 2h. Oh, this is just the same information, right? Yeah, I just duplicated the same information. Consider the time interval from when the two carts are released until just after they collide. Okay. For the system consisting of the two carts and the Earth, indicate whether the total mechanical energy increases, decreases, or remains the same. Okay. So, since it includes the Earth, this is what this whole question, these two questions are all about. Since they include the Earth, in this one they include only the two carts, then the mechanical energy is conserved, because the mechanical energy in this case is their potential and their kinetic. Well, they're going to trade one for the other, right? Whatever they have potential is going to turn into kinetic. And they're going, so this car's energy, mechanical energy, will not change as it goes down. After the collision, it might change because of frictional losses in the collision, but particularly if it's an inelastic collision. But from here to here, its mechanical energy stays the same because it includes gravitational and kinetic. So remains the same. And I remember the first time I saw this question. I have seen this one before. And this is, to me, it was a very annoying question. But once you realize what they mean, it's not hard. Then they say, for the system consisting of only the two carts. What they mean is, now, forget the Earth even exists. The Earth is an external force. It is not part of the deal. So you don't get to count potential energy as mechanical energy. The only thing in mechanical energy is kinetic energy. When you word it like this. Well, does their kinetic energy stay the same the whole time? It's zero here, and it's a lot here, right? And it's zero here and a lot here. So the mechanical energy for the system would increase because the mechanical energy would be affected by an outside force, gravity. It's just a game with words. So you'd have to say something about mechanical energy would just be the kinetic energy of the blocks, of the carts, I mean. And we see that both experience an increase. So they increase mechanical energy. But if you consider the Earth, yeah, they lose gravitational, but they pick up kinetic, but the total mechanical energy, the sum of the two, stays the same. So that's why you would say this.